Hello, my name is Nikita Bogdanov, and I'm currently a senior at Albuquerque Academy.
My name is Evan Liu, and I'm currently a junior at Olympiad Academy.
So today we're going to be filming our Mission Possible device from the 2011 Science Olympiad competition. The goal of this event was to construct a Rube Goldberg device, starting with the dropping of a quarter and ending with the release of a pre-filled and tethered helium balloon. There were a minimum of 8 tasks out of a list of 13, which could be additionally included in the device. And for this particular device, we chose to include the high scoring tasks in order to maximize our points. So the starting task for Mission Possible is to drop a quarter and setting off a mousetrap. Now in our device we have the starting task leading into task L, which is to stack 5 wooden blocks no smaller than 5 centimeters by 5 centimeters by 2 centimeters, such that the stack of 5 blocks causes the next action and that they're not touching in their unstacked state. We can go ahead and set this up here. What this block stacking device does is it keeps all of our blocks separate by means of this weather stripping, and when the mousetrap snaps, it releases the tension on the cord, allowing this device to open up, dropping all of the blocks. When the blocks drop, the heaviest block with weight is on top such that it will trigger a switch, and that switch will depress and lead to the next action. You can see here the blocks are in their setup state. So here's the initiating step of dropping the quarter, which will stack the blocks and turn on a fan here. 3, 2, 1, drop. The fan propels this car by use of the makeshift sail from a wayboat, allowing this ball to roll down a ramp and hitting this mousetrap. This is one of the required tasks to use wind or air in order to cause the next action. Now, the hydraulics task is what's followed here, and what we do is this mousetrap is actually keeping pressure on a hydraulic system. So in setup, this bolt here will squeeze the hydraulics cord, not allowing any pressure to go, and activate this switch, which will turn off the fan and begin the next task. So you can see here that when I press this in, the switch is not activated, and we have a rubber band that makes sure that pressure is constant on here. And once the ball falls, we then have the fan turning off. Now, when the switch is depressed, it turns off the fan and starts the next task, which is to convert circular motion to linear motion without the use of gears, and to use the linear motion to cause the next action. So what we have here is that this spinning disc with a straw on it will propel the ball forward and cause it to snap this mousetrap here, leading to the next action. Now, the next task that we have here is to initiate an enclosed chemical reaction that creates a gas, and to use that gas to cause the next action. Now, what we have here is a chemical reaction between baking soda and vinegar, where the vinegar is contained in this upper container, and the baking soda is then held in the container below, marked I, number 2. The vinegar is allowed to flow into this container when the mousetrap previously described pulls off a rubber band from the tube. Now, what this does is it creates CO2, which will then inflate a balloon inside of this contraption, depressing a switch. And just to give an example here, I can blow into the top, simulating gas entering the system, and the switch will then be heard as being depressed. So the balloon described in the previous task here is pressing a switch which will cut current to the next task. The object of this task is to decrease an object's temperature such that the change in temperature causes the next action. Now what we do here is using a bimetallic coil from an oven thermometer. We pass current through it by contacting it to a wire right here. By doing so, the coil is heated, and once the balloon starts up and depresses the switch, current is cut to the coil and turns on a cooling fan, which will cool down the coil away from this contact. When the coil comes away from the contact, it will switch a relay, and this relay will then turn on a motor here, which will fling a ball into this mousetrap right here, setting off the next action.
So the ball comes from this task and hits this mousetrap, which will be set, and the string that is attached to this mousetrap will loop from under the board over the top into the sand timing funnel. So there is a glass tubing inside the funnel, and this part of the string fits perfectly inside the glass tubing. So when this mousetrap is released, sand will then be able to flow down through the funnel into this cup. So a steel ball bearing is placed behind this white cup of the sand timing, and when the funnel opens, when the string is pulled, the sand will fall from the funnel into this cup, and the balance will shift from this cup to this cup, allowing the steel ball bearing to fall. After that, it will hit this mousetrap, and this mousetrap will be connected to the balloon tether, which is this pink strip you see right here, and so then this will release the balloon, and the helium balloon will rise. So this happens after this steel ball falls.
Here is the setup and full run of our Mission Possible device. We're going to be using a calculator to determine a random integer within the given range shortly after setup, and this is going to tell us how long we should aim for the device to run from start to completion.
So the calculator gives us a generated value of 66 seconds, which will be our target value for the total time of the device running. It is important to remember that we're aiming for anywhere between 66 and 67 seconds, as the competition gives full points for every full second.
Okay, so we're going to be starting the device here. Just one last minute heating of our temperature test coil because it is time sensitive. The stopwatch here is running, and we're just going to take the difference between times. Here we go in 3, 2, 1. sand is going.
Where's that fantasy going?
Okay, so the sand time was 1 minute and 91 centiseconds.
So, here we have 1 minute and 22 seconds for the whole device runtime. I'm going to explain what happened and why we had issues. So, everything from pretty much from the start quarter drop task right up to the temperature task here actually worked perfectly, and everything was timed quite well. The only issue here was that one of our batteries, which control this motor right here, were actually disconnected or out of juice, and so when the tasks proceeded up to the temperature task, the motor didn't start, and because of that we were off by about 22 seconds. And as you can see, the sand time is actually pretty accurate. It's really just pausing here and my waiting to see if anything would actually happen, and in the end I had to just manually advance that. Other than that, the sand time was good, and the balloon release was perfect, and it remained tethered. No objects really exited the device except for one of our shields here, but other than that, it was a pretty good run.